Johnstone here. We'll speak about Topos-theoretic models of the continuum. This is the one talk that is a full hour, and again, 10 minutes of questions after that.
Okay, thank you. At the last meeting in January, it was suggested that it would be helpful to have a talk about how Topos theorists view the continuum to see whether this is actually of any use to quantum theorists. I have to confess I'm not sure that it is. And in particular, and this may be a disappointment to some of you, what I'm going to say has absolutely no bearing on the problem of the Planck length, the possibility that the sort of very small scale structure of space-time may be different from its macroscopic structure. And there is a perfectly good reason for that. It seems to be a question that you can't possibly hope to address with the sort of models that we have, because whatever my model of a real line, I'm going to talk about several different ones which have different properties, and you can choose your model to suit the properties you want. But one thing they all have in common is that they are all, at the very least, modules over the field of rationals, which means that rescaling is going to be an isomorphism of whatever structure they carry. Let's say multiplication by n, enlarging by a factor of n, is going to have an inverse, multiplication by 1 over n, and so you cannot tell the difference between the macroscopic and the microscopic structure of the continuum. If you want to do that, then you've got to start with something that isn't a module over the rational, and I don't know any Topos-theoretic model of a continuum that doesn't have at least that much algebraic structure built into it. Well, in fact, of course, any constructive model of a continuum is going to have algebraic structure built into it. It's going to be, at the very least, a ring. If I just draw a line on the blackboard, there's no ring structure visible there, but the moment I choose a point, then the other points on the line become associated with lengths, so x becomes associated with the distance from 0 to x, and of course we can add lengths, and we can subtract lengths, so that gives us an additive structure. And once I've chosen the second point, call it 1, I then have ratios of lengths, and by the elementary geometric constructions involving similar triangles, I can multiply lengths. And it's very easy to prove constructively that these geometric constructions that you perform are going to give you the structure of a ring. So any model of the real line that I'm going to be interested in will have ring structure built into it. It will also quite visibly have an order structure. It makes sense to talk about one point being to the left of another. Of course, I'm not claiming that that's a total order. I don't claim that I can distinguish whether one point lies to the left of another, but certainly there are cases when I can tell, and I want to be able to analyse those in terms of the order structure. So any model of the real line will have the structure of, at the least, an ordered ring, and of course other structure comes with that. You get a topology by considering the open intervals as the basic open set, and all of these things should be present, but their precise properties will vary according to which model of the reals you're looking at. And the models fall into two distinct classes. There are what I might call constructive models, where you try to construct the reals, you try to take some classical construction of the reals and perform it in the non-classical context of a topos. So the idea is that in your topos you have some model of the natural numbers, and there is really no dispute about what that is. Bill Lovio told us how to recognise the set of natural numbers categorically, and a topos either has a natural number object or it doesn't. If it has one, you can then hope to carry out the construction of building from that the integers, the rationals, and finally the reals. And so I'm going to talk about those approaches first, but there are also axiomatic approaches where you start by deciding what properties you want your continuum to have, postulating those, and then looking for particular toposes in which rings with that type of structure exist. So I'm going to begin with the constructive approaches. I'm not sure if this will work on this machine. Let's see. Right. Never mind. So the first idea you might have is to model is to copy the construction of Dedekind cuts, and the first guess you might have is to do it in a one-sided way. That's to say, just identify each real number with the set of rationals that lie below it. And so you look at certain particular sorts of subsets of the rationals, lower cuts. So these are sets which are closed downwards. They're open at the top end. That's what the second and third of those axioms say, and also inhabited. And you would like one further condition. You would like the complement to be inhabited as well, but because we're in a non-classical context, that axiom has to be separated out from the others. These first three are all what we call geometric axioms. That's to say, their validity is preserved by continuous transformations of toposes, what we call inverse image functors. So those three live in a different fragment of logic from this final one, and there are good reasons for separating them, which we'll come to in a moment. So in any topos you have the structure available to build the set of subsets of the rationals. Well, if you've got the rationals, and as I say, if you've got the natural numbers, the construction of the integers and the rationals is completely straightforward. It's just like the classical construction, and there's no possibility of doubt there. And you end up with a structure which is a field in the strictest classical sense. It's decidable. You can tell whether or not two rational numbers are equal, and there's no room for doubt about what the rationals are. But then when you go to the power set of the rationals, of course, the non-classical logic starts coming in, and so this structure has properties that are different from what you might expect classically, and in particular, the difference between the first axiom and the fourth is crucial to this. So how can we identify what we get if we try to build this object in a topos? Well, if we ignore the fourth axiom for the moment, what we have there is, as I say, a set of geometric axioms, which means we have what's called a geometric propositional theory, and we can build the so-called classifying topos of the theory, which is the topos containing a model of the theory which knows nothing except that it is a model of the theory. The objects of the topos are entirely built out of that model. And what you end up with, it's a spatial topos. You end up building a frame, that's a complete Heiting algebra, generated by symbols which I denote as being semi-infinite open intervals. But this corresponds to the proposition that a particular rational number p belongs to the lower section L. In other words, that L represents a real number somewhere between p and plus infinity. And then these symbols satisfy certain axioms, which are just derived in a completely straightforward way from these three axioms for the real line, for the Dedekind sections. So the first one says that these open intervals are ordered in the way you expect them to be ordered. When you take the intersection of two of them, you get whichever should be the smaller one. And then the other two, well, this axiom corresponds to axiom 1 up here, saying that every real number is greater than some rational, and this one corresponds to the third axiom, which says that these things are open at the top, that the Dedekind cuts are open at the top end, so the interval from p to infinity is the union of all the strictly smaller intervals from q to infinity. So that generates a frame, or an abstract open set lattice. In this particular case, it is spatial. That's to say, it can be represented as a lattice of subsets of its space of points, and its space of points is precisely this set RL+. So we can view these as being actual subsets of RL+, the sets of sections satisfying the condition that they are greater than a particular that they contain. contain a particular rational P. And so this gives us what's called the classifying topos, or the theory of these one-sided cuts, taking sheaves on this space, which means that models of the theory in an arbitrary topos correspond to continuous maps from that topos to RL+. So in particular, if you're looking at the topos of sheaves on any space, they just correspond to continuous maps from the space to RL+, equipped with this topology, in other words, to lower semi-continuous functions from X to the standard real line with the point at infinity added. Now, the reason why this last axiom is awkward is that it's not geometric. Clearly, if you add that axiom, you get a subset of RL+, which is called RL, and that is indeed a certain subset of the lower semi-continuous functions, but it's not what you would like it to be, namely just those functions that never take the value of infinity. It's those functions which are locally bounded, and that's stronger than just not taking the value of infinity. So there's a slight delicacy there. In particular, the notion of a lower semi-continuous function which is locally bounded is not invariant under continuous change of base, whereas this is. So one disadvantage of these one-sided cuts is that it's rather hard to exclude plus infinity. The other and more serious one is that although you get some of the algebraic structure, of course you can add one-sided cuts, you can't subtract them, so you don't have a ring structure there. So in order to do something constructively that will give you a ring structure, you need to use two-sided cuts, that's to say pairs of cuts, one being a lower cut such as we had on the last slide, and the other being an upper cut. And so here is the definition. We take there it is. We take pairs of subsets of the rationals L and U. I can't read that because it's reflecting. So the first four axioms say, the first six axioms say, L is an inhabited lower section, just as we had on the previous slide, and U is the dual thing, an inhabited upper section. And then finally we want to say L and U are disjoint, and they're as close together as they possibly could be. And the way we say that in a geometric fashion is to say that if X is less than Y, then either X belongs to the lower cut or Y belongs to the upper cut. So that there might be a single rational missing if this is the pair that actually represents a rational, but there can't be two distinct rationals missing from the union of L and U. One or other of them must be in either L or U. Well, again, those are geometric axioms, so they correspond to a classifying topos, which again corresponds to a frame, and this is called the frame of formal reals. So here, the primitive symbols, well, you could take primitive symbols of form P infinity and minus infinity Q, but the intersection of two of those is going to be things like I can denote PQ, and just think of it as a rational open interval, and they suffice to generate the frame. And then the axioms that they satisfy are, firstly, that if you take the intersection of two of them, they intersect in the way that you expect open intervals to intersect. Secondly, that they cover the whole real line. That's to say that, so this corresponds to saying that every real number is greater than some rational and less than some other rational. And also that each open interval is the union of all the strictly smaller open intervals. And notice I smuggled in there something that you might have expected me to tell you at the beginning, namely that if P is greater than or equal to Q, then the open interval PQ is empty. So that's a particular case of the axiom above, because there will then be no pairs R and S satisfying those three inequalities. And finally, the last axiom. So this corresponds to the second last axiom that we had for the pairs of cuts, and this one corresponds to the last axiom, which says that if I take two overlapping open intervals, so P less than or equal to Q less than R less than or equal to S, then the union of PR and QS will be, sorry, that should be PS there, apologies. So here we have a frame and we have a locale having listed its frame of open sets, and I write RF for that formal space or locale, and we'd like to know once again. Well, we do know that models of this theory in any topos will correspond to continuous maps into the topos of sheaves on RF, but the question is that, well, okay, let's, yes, coming on the next slide. Sheaves on this is a classifying topos of two-sided Dedekind cuts, which means that in any topos defined over the topos in which we construct RF, models of the theory of two-sided cuts in that topos will correspond to continuous maps from the topos to RF. So in particular, if X is, if the topos is sheaves on a space, they correspond to continuous maps which will have to factor through the space of points of RF, and the space of points of RF is just RD, this set here, equipped with the topology generated by the rational open intervals. However, that does not answer the question of whether RF itself is a space. In other words, is it isomorphic to RD? So this is the first point at which this constructive theory shows a sharp difference from the classical theory. So is it the case that our constructive real line really is made up of points? Or is it, or could it have more in it than the points can detect? Well, as I've already said, RD is the set of points of RF. So in particular, when I equip it with the topology generated by the rational open intervals, it's a sober space, which is a good thing to have. But is it actually the whole of RF? Well, you can prove that using the Heine-Borel theorem. The proof is messy, so I haven't written it out, but it's completely straightforward. But you do need to know at one point that where you've got a covering of some open interval, you need to know that you can reduce that to a finite covering. A covering of some bounded closed interval, you need to be able to reduce that to a finite open covering. So you need the Heine-Borel theorem that bounded closed intervals are compact. So you need that to hold for the space RD. Now, the Heine-Borel theorem, it's often presented in elementary textbooks on analysis in a way that seems to imply it uses at least countable dependent choice. It doesn't. It's an entirely choice-free proof, so it holds in any Boolean topos. So this isomorphism is valid in any Boolean topos, and in fact, we can say more than that, in any topos, in any Grothendieck topos with enough points, in other words, any topos that's been covered by a Boolean topos. This isomorphism holds. However, it doesn't hold in general. It is essential that Heine-Borel should hold, because you can actually prove for the formal reals, for the locale, that locale is locally compact. In other words, if you take any closed interval, I've suggested taking 0, 1, that closed the closed sublocale you get by by adjoining the relations that say that all these intervals are empty, that closed sublocale is compact constructively. So if this isomorphism holds, then the space RD must be locally compact as well. In other words, the classical Heine-Borel theorem must hold. It was shown first by Mike Foreman and Martin Hyland, and subsequently a much more elegant proof by Unger Joyal. The Heine-Borel theorem can fail constructively. There are Grothendieck toposes in which it fails. Joyal's construction is a particularly elegant one. What he does is essentially to take the theory. He makes the idea of an open covering of 0, 1 with no finite subcover into a geometric theory, and he then takes the classifying topos of that, shows its consistent theory, and moreover, that in the topos, in the classifying topos, you do end up with a covering of 0, 1 with no finite subcover. So there are toposes where the Heine-Borel theorem fails, and therefore also the real line considered as a locale. So if you just take it in terms of that presentation we had on the previous slide, that presentation doesn't define a space. So that's one aspect of the non-classical possibilities that you have for the real line in a topos, that it might be the case that it is a space, but that is, a locale, something that has continuity properties, but is not entirely resident on its points. Now, of course, the theory of locales is often unkindly described as pointless topology. Well, what's going on here is not pointless at all. I mean, the locale does have lots of points. RD certainly contains all the rationals, and lots more besides. It contains root 2 and e and pi and all those familiar real numbers. All of those are certainly perfectly constructive things that you can define, but they don't give you enough actually to describe the open set lattice that you want to describe, or they may not. So that's one possibility. Incidentally, yes, I should mention this, that you can actually prove not only is the spatiality of RF equivalent to the Heine-Borel theorem, it's also equivalent to saying that under addition, the spatial reals form a localic group. Rather strange condition, but the point is, I haven't yet told you how to add and multiply Dedekind reals. I will do in a minute. But there is a notion of addition. It is continuous in the topological sense as a map from RD cross RD to RD. If you want it to be continuous in the localic sense, that's a stronger condition, and it forces RD to coincide with RF. And I've noted that RD is always a spatial group. That's to say, the addition is always continuous in the spatial sense. If you want it to be continuous in the localic sense, it has to coincide with the formal reals. Okay. So that's one approach where we actually seek to construct our real numbers, and it does have this problem that we may end up with something that is a space that can't actually be described by its points. There are other approaches, and one that many people might like to work with is the notion of Cauchy sequence. So why not use Cauchy sequences instead of Dedekind cuts? Well, we can certainly do that. We can form. So here is the set of all Cauchy sequences of rationals. I take my Cauchy sequences to converge at a uniform rate, so I demand that the distance between fm and f of n should be bounded by 1 over whichever is smaller of m and n. That's just a technical point. It doesn't make any difference to the construction, but it makes the construction a bit easier. And then you have to factor out by an equivalence relation, and it turns out that's the equivalence relation you need to identify two Cauchy sequences if f of n and g of n are always within 3 over n of each other. That forces them to be converging to the same point. And that is actually an equivalence relation, although it doesn't look like it. So you can form a quotient, and you get another object in your topos which looks as if it might be a candidate for a set of real numbers. Obviously, the rational sits inside this model because any rational can be represented by a constant sequence. It's also easy to associate with every Cauchy real a Dedekind real. You can work out whether rationals are less than or greater than the limit of a Cauchy sequence, and so you can partition, or not quite partition the rationals, but you can define those two Dedekind cuts associated with a Cauchy real. And the second inclusion is an isomorphism. That's to say, every Dedekind real is a Cauchy real, provided you have countable choice. Obviously, if you have a Dedekind real, then you can always find a rational within 1 over n of it, using the last axiom for Dedekind reals. But you have to do that for every n simultaneously, and that's going to involve choice. So there are toposes, non-trivial, non-classical toposes where countable choice holds, the effective topos being one example, but it doesn't hold in general. So this in general is going to give you a smaller set of real numbers than the Dedekind construction, and it's a less satisfactory set because it sort of behaves unpredictably. Well, not unpredictably in the sense that we don't know what we're going to get in a particular topos, but it sort of behaves inconsistently, would be a better word. So to take two rather similar looking examples, if I take sheaves on the classical real line, so I'm assuming I start with a classical topos of sets and I have a space in it which is the classical real line, in sheaves on there, we already know that the Dedekind reals is the sheaf whose sections over U are all continuous functions from U to R, whereas RC is much smaller, it's just the sheaf of locally constant real valued functions. On the other hand, if you cut down to sheaves on the rationals, as a subspace of the reals, you get the sheaf of all continuous real valued functions, all continuous functions from open subsets of rationals to the reals. So in that case it coincides with RD. Well, that's because countable choice holds in sheaves on Q, but it fails in sheaves on R. So just making a very small difference to the base space produces a big difference in what that object of Cauchy real numbers looks like.
So what's a locally constant function from R to R?
A function which, well, if it's defined on the whole real line, it's a constant function because R is connected. But I'm saying locally constant real valued functions defined on open subsets of R. Okay. And the other nasty thing is that if you construct the open set lattice of RC, it is actually isomorphic for the open set lattice of RD. So RD, since we know RD is sober, RC can't be sober unless it coincides with RD. So topologically, the Cauchy reals are bad, and if you try to make them good, you end up generating the Dedekind reals anyway. This in particular seems to me to indicate that the Dedekind reals are preferable to the Cauchy reals in almost all contexts where they, well, certainly in all contexts where they're different. It is sometimes, in the effective topos, it is more convenient to work with Cauchy reals because they're easier to handle in that context, and they do there coincide with Dedekind reals, so you don't lose anything by doing that. But if there is the slightest possibility they might be different, then the Dedekind cuts approach is the right one to choose. Now, at this point, when people talk about the Dedekind reals and the Cauchy reals, there's usually some smart aleck in the audience who asks, why not use continued fractions instead of Cauchy sequences? And then you don't have that nasty equivalence relation around. Well, the continued fraction representation of the reals is a very beautiful object, classically, but constructively it's completely hopeless. And the reason is that there are really two different sorts of continued fractions. There are finite ones and infinite ones, and you can tell them apart. So if you try forming, you can perfectly well form an object of continued fraction representations of reals in your topos, but the problem is that the sub-object of that, which corresponds to the rational continued fractions, is complemented. Well, in some cases that would be all right. For example, in sheaves on the reals, if you take the locally constant real valued functions, Q is the sheaf of locally constant rational valued functions, and that does have a complement, namely the locally constant irrational valued functions. So in this topos you've got no problems, but in this one it's something very nasty indeed. The complement of the sheaf of locally constant rational valued functions in the sheaf of continued real valued functions is something very strange indeed. And if you take the union of, the pseudo-complement, and if you take the union of Q and its pseudo-complement, or Heinting negation, you end up with something that is, as I say, very strange indeed. And we can't even add continued fractions. If you're given two rational continued fractions, of course you can add them. You can add a rational to an irrational, fine. But if you try to add two irrational continued fractions, you have to decide in advance whether the answer is going to be rational or irrational before you know what it's going to look like. And that, constructively, is obviously impossible. So the continued fraction expansion idea, although superficially attractive, is not worth pursuing. Okay. So let me now say something about order and algebraic properties, which I mentioned already that we should have those. So how do we define them? So there are two different ways of defining the order relation. I should say that all of this can be done for the Cauchy reals as well, and you get essentially the same things happening. But I'm not going to talk about those separately now. So the idea is that x should be strictly less than y if we can find a rational that lies in between them. So that's what the first one says. If there is an x which is to the right of the first real and to the left of the second real, then we can definitely say that x is less than y. And to say x less than or equal to y, we say that everything less than x is less than y, or equivalently, everything greater than y is greater than x. So we have a strict and a weak order relation, and they satisfy some properties that look sensible. The weak order relation is the negation of the strict one. So x less than or equal to y is equivalent to the negation of y less than x. But of course, that doesn't say that y less than x is the negation of x less than or equal to y. It isn't, in general. And there's also a ring structure, as I've mentioned. Constructing the ring structure on R, or on the Dedekind reals, in a constructive context is trickier than you might at first think. The addition is fine, no problem with addition, but multiplication, when you multiply Dedekind sections classically, there is a subdivision into cases. You need to know whether you're multiplying two positive reals or two negative reals or zero, and we don't have that. You know, the order on the reals is not decidable, so we can't make those decisions. So there is some subtlety about how you define multiplication of Dedekind sections constructively. It can be done, and it's rather technical, and I'm not going to tell you how to do it. Just believe that it can be done, and it does make the Dedekind reals into a ring, as they should be, and it's a ring in which the invertible elements are precisely those that are either strictly greater than 0 or strictly less than 0. So it follows that to say x is not invertible is the same as saying that x is less than or equal to 0 and x is greater than or equal to 0, which of course, this relation is clearly antisymmetric. That's equivalent to saying that x is equal to 0. So we get this condition, that R is a ring in which the non-invertible elements, the only non-invertible element is 0. And that's one of the ways of defining what it means for a ring constructively to be a field. This is what, in an old paper, I call the residue field, because it's what you get if you take the residue field of a local ring constructively. In particular, this tells me that R is a reduced ring. It has no nilpotence. Because if x squared is 0, then certainly x is not invertible, and therefore x must be 0. It's also a local ring in the constructive sense, which means that for every x, either x or 1 minus x is invertible. That's very easy because we already know that for every x, either x is greater than 0 or x is less than 1. So that says either x is greater than 0, in which case it's invertible, or 1 minus x is greater than 0, in which case it's invertible. And it satisfies various other nice things. Every positive element has a positive square root, in fact a unique positive square root. And indeed it satisfies the axioms of what are called a separably real closed local ring. This is the constructive analogue of the notion of real closed field, if you like. It's not a field in the constructive sense, in the strictest constructive sense. It's only a local ring and a residue field, but it is separably real closed, which is a constructive way of, a geometric way of axiomatizing the notion of a Henselian local ring with real closed residue field. So it's as close to being a real closed field as it can be, given that it's not a field. So algebraically, it's a nice gadget. The order relation, on the other hand, is not quite as nice as it might be. We can form binary max and min in a fairly obvious way. To form the max of two Dedekind cups, we form the union of their left sections and the intersection of their right sections, and so on. So in particular, we have the absolute value function. Max of x and minus x exists, so we can form the absolute value of x. But we can't form subs and infs of infinite subsets in general. It isn't, well, it's certainly not order complete because it doesn't have endpoint, it doesn't have plus or minus infinity there. But we might hope for it to be conditionally order complete, which is to say that every inhabited bounded subset has at least upper bound, and that's not true. We can remedy it. There's a modified version of RD called Rm, M standing for McNeil because it's actually the McNeil completion of the rationals, which does achieve conditional completeness, but it loses the good algebraic properties. In particular, it loses the property of being a local ring. So this is another case where you pay your money and you take a choice, but for practical purposes, the Dedekind reals are more convenient to work with in almost every context, and McNeil reals are there if you need completeness. The relationship between the two is quite well understood. You can reconstruct the McNeil reals from the Dedekind reals by taking what's known as the Gleason cover of the topos and simply pushing the reals down from the Gleason cover. But I don't want to go into that because basically the extra properties you get by passing from RD to RM are of relatively minor importance. Then the next thing I wanted to talk about was the question of whether all functions from the reals to the reals are continuous. Now notice, incidentally, we've rather lost sight of the fact that RD might not be the good guy. We might actually want to work with the locale, the formal reals, rather than the space, rather than its space of points. But of course it doesn't make sense to ask the question, are all maps from the formal reals to the formal reals continuous, because the only maps we can talk about between locales are the continuous ones. So this question has to be asked about the space of reals, where in theory we can look at arbitrary maps from the reals to the reals. Excuse me. And we can ask, are they all continuous or not? Of course, Brouwer advanced arguments why constructively one should expect that all the functions you can actually define from the reals to the reals should be continuous. So it would be nice to know whether that holds, or whether it could hold in a topos, and indeed it can. Martin Hyland gave an argument to show that it holds in the topos of sheaves on the reals. That's a slightly ad hoc argument. There's a better one. I'm not sure who it's due to. It's expounded in detail in the book by MacLean and Moerdijk. But it holds in what's called the gross topos, where what you do is take sheaves not on a single topological space, but on essentially the category of all topological spaces. Well, you can't do that because that's a large category. You take a large enough subcategory containing the real line itself and the function space, R space of all continuous maps from R to R with the compact open topology, and you equip this category with the Röhmlich topology generated by open covers. That's a jointly surjective families of open inclusions. That gives you a category of sheaves, and in there it turns out that the Dedekind reals is just the sheaf represented by the classical space of reals as an object of that category, and the exponential is just represented by the space of all continuous maps from R to R. So the fact that every element of RD to the power RD is a continuous map from R to R is sort of built into the construction of this topos. I mean, it does require proof that this axiom actually holds in the internal logic of the topos, but it's once you've got these identifications, it's not difficult. I said you should use, strictly speaking, you should consider C as a subcategory of the category of locales, because if you're being constructive, we've already said that R, the space R, may not be locally compact, and this identification depends on the fact that this thing is an actual exponential in the category of topological spaces, which it will be only if R is locally compact. So if R is not locally compact, you need to work with locales where R is locally compact and it is exponentiable, and so this works. But that doesn't affect the rest of the argument. In sheaves in the ordinary topos of sheaves on the reals, the argument goes rather similarly. We know there that the dedicated reals is just a sheaf of continuous real valid functions, and what you have to show is that R to the R is the sheaf whose sections over U are all continuous functions from U cross R to R. And that identification, as I say, there's a clever trick that does that, but it is a clever trick, whereas this sort of comes directly out of the structure of the category. It's forced by the category you're working with. Okay, and Andre Chayal showed, once you know there is some topos where the continuity principle holds, there is a gluing argument that shows it holds in the free topos, let's say the topos freely generated by nothing at all. So there are toposes where we can have this principle. And something that's worth pointing out, continuity principle implies that R is indecomposable in a pretty strong sense. You can't break it into two pieces, each of which is inhabited. Because it is connected, topologically connected in precisely this sense. You can't break it into open pieces with those properties. And the continuity principle tells you that if you could break it into two pieces at all, then you get a characteristic function, a map from R to 0, 1, which was 0 on A and 1 on B, and therefore A and B would have to be open, because that map would have to be continuous. So this says that the continuum coheres in a very strong sense. And that seems to be a desirable property of a constructive continuum, that it should be something that you can't split apart without losing anything. So that's, I think, a valuable aspect of it. Now, moving on, I've talked for probably too long about constructive approaches to building the continuum in a topos. There are some things we might want to do which we can't do with any of those constructive approaches. And one is, suppose we want something stronger than Brauer's theorem, suppose we want every function R to R to be differentiable. I said or even smooth, but of course if every function is differentiable, then every function is infinitely differentiable because its derivative is differentiable as well. So suppose we wanted that. Physically that's a reasonable thing to demand. Discontinuous functions don't exist in nature, but functions with discontinuous derivative don't exist in nature either. But that is impossible with the Dedekind reals because, as I mentioned, we do have the absolute value function there, and that's certainly not differentiable at x equals 0 for any reasonable sense of the word differentiable. We can realise it axiomatically, but it seems to require that our ring of real numbers should have nilpotent elements in it. At least any realisation of it that's known to me is based on the idea that there are elements of square 0 in the real line, and we also saw that the Dedekind reals doesn't have elements of square 0. So, solution, which was first proposed in 1967 by Bill Bourvier, was to just consider what axiomatic properties you would like a ring of smooth real numbers to have, and then, once you've worked out the theory of that, look and see whether models do exist in suitable toposes. And so the key axiom that Bourvier isolated was this one here. So we look at the set of elements of square 0 in R, and we say is that every function from D to R should be uniquely expressible in the form D maps to A plus BD. So in other words, it should be uniquely expressible as a linear function, or affine perhaps would be a better word, of the variable D. So that, notice that implies that there are non-trivial elements of square 0, because otherwise the coefficient B wouldn't be uniquely defined. But this axiom is actually incompatible with classical logic. But it turns out that it's surprisingly easy to find models in toposes. But anyway, the point about this axiom is that it then immediately tells you you've got a function from R to R. You can define its derivative by saying, well, if I restrict it to elements of form A plus D, where little d is in capital D, that gives me a function from D to R, which must be linear, and so the slope of that line must be the derivative of f at A. So that immediately tells you that every function from R to R is differentiable, and therefore infinitely differentiable. Well, as I say, models for this axiom are much easier to find than you'd expect, and the generic local ring is an example. So if you just take the theory of local rings as a geometric theory, it has a generic model which lives in a certain category of pre-sheaves on finitely presented rings. The generic ring lives in pre-sheaves on finitely presented rings, and then you impose a topology on that to get the generic local ring. Actually, we do want our ring of smooth, our smooth real line to be at least an algebra over the rationals, as before. We want to be able to divide by, we want to be able to, if we want to form Taylor expansions of functions, we want to be able to divide by any positive integer, because Taylor expansion involves 1 over n factorial, and so on. So we want it to be at least an algebra over the rationals, and we might as well make it an algebra over the classical real line, classical field of real numbers. Algebraic and order axioms. Well, we certainly want R still to be a local ring, and indeed separably real closed, local. That's that property that I mentioned, which holds for the Dedekind reals in any topos. We want it to be as close to being a real closed field as it can be. And actually, there is a simple way of achieving that, which is by demanding that it should be not just a ring, but what's called a C infinity ring. This is a concept, I'm not sure who first invented it, but it is now standard in synthetic differential geometry. The idea is that you should take as algebraic operations on your ring not just all polynomial functions, as you would. So an R algebra is something in which you can interpret any polynomial in any real polynomial in n variables as an n-ary operation. What you do here is you allow us to interpret any smooth function of n variables as an n-ary operation on the ring. So in particular, polynomials are smooth functions, and so you get the ring structure, but you get more. And then, if you have one of those things which is local, it's automatically separately real closed. We have to lose the residue field property, which I mentioned earlier, because we've now got nilpotence, and the residue field can't have nilpotence. But it can satisfy the dual axiom, which says that the non-zero elements are exactly the invertible elements. We want an order relation which will satisfy things like the condition that the invertibles are precisely the things that are either strictly positive or strictly negative. And then we define the weak order relation to be just a negation of that. We don't need to postulate it. But notice that this is now only a pre-order, not a partial order, because every nilpotent is going to be both greater than or equal to 0 and less than or equal to 0. So those are some of the things we might want our ring of smooth reals to have. Oh yes, surprising remark at first sight. These axioms imply that the strict order relation now is double negation stable. Not x less than y implies x less than y. and there's the proof. See, because invertibility in a field of fractions is double negation stable, and invertibility is just one, well, this is just one half of invertibility, it necessarily acquires double negation stability as well, which is sort of unfortunate. That's something that makes me feel uncomfortable, but it's true. And something that Jim Lambeck has recently pointed out, that there is another approach to what we mean by infinitesimals, suggested by Jacques Penon. So Bill Mauvier's idea was to regard the nilpotent elements in the real line as being the infinitesimals, and Jacques Penon said, well, we could define them purely in logical terms as saying that those elements which are not equal to 0. And the axioms that I gave you on the previous slide tell you that these elements form an ideal, and it is exactly the Jacobson radical of the ring, whereas the prime radical is precisely the set of all nilpotents, which are the ones that Lauvier and Comte considered. So we can find models for this axiom system in relatively simple toposes. They take a bit of work to construct, but of course then the question is, in those toposes you also have the ring of Dedekind reals that you can construct starting from the rationals. How do you compare the two? Well, here's the result. Now I mentioned that since I agreed to give this talk, I've been sent 2 recent preprints, one by John Bell and one by Jim Lambeck, which have quite a large overlap, and between them they prove the following result. That I don't know whether I do know they're aware of each other's papers, but they appear to be written independently. So if we suppose that, in addition, that our ring of smooth reals is Archimedean, in the sense that the natural numbers are cofinal, so every smooth real is less than some natural number, then if you factor out the Penon-Jacobson radical, you're just going to end up with the Dedekind reals. And moreover, that, of course, since the smooth reals are a field of fractions, this will force the Dedekind reals to be a field of fractions. So in other words, it will force the strict order relation on the Dedekind reals to be double negation stable, which is very strange and not something you expect. Well, as I say, this can happen in examples, but it's actually much more common to find that the natural numbers get slightly enlarged in these models. So you have the constant natural numbers, and then you have the smooth natural numbers. So somehow there are smooth natural number functions which are not constant. And you need to use those. So in order to get all the way up to the top of the smooth reals, you need to use those. And then when you form the quotient of the smooth reals by the Penon radical, you get something that contains Dedekind reals as a subring, but not the whole thing. So it's a subring of a quotient of the smooth reals. So there are ways of building models of these axioms, but they're all sort of slightly problematic in that one is building this large infinite object, and it's not clear quite where you're starting from. Bill Lauvier recently pointed out a very interesting idea, which at the moment is still rather unformed, which is you might actually be able to get away with simply axiomatizing not the whole real line, but just that little infinitesimal object d, and build the real line from it. Because although d itself is, in comparison with the reals, it's tiny, it's so small you can't, the naked eye can't distinguish it from a point, although it is different. But the exponential d to the power d is actually quite large. And specifically, because it's a monoid under composition, and it contains the multiplicative monoid of the reals as a retract. In fact, as a submonoid, of course, d to the d is a non-commutative monoid, and R appears just its centre, that's to say, the set of elements that commute with everything. as a quotient, well, Bill claims in a paper that I've seen that it's the abelianization of d to the d. That's to say it's the quotient by the smallest congruence that identifies all pairs FG and GF. I've not been able to prove that, and I don't know whether Bill actually has a proof of it, or whether he just believes that it ought to be true. I mean, clearly it's a quotient by a congruence that certainly contains all those pairs. Whether it is the actual abelianization, I don't know. So in this way, one could start with D and recover at least the multiplicative structure of R from the object D to the D, and at least in theory, there are ways where we could get the additive structure back as well. The addition can be characterized as the unique D homogeneous map from R cross R to R, where D homogeneous is a technical concept that I'm not going to define. So in principle, there is this possibility that one could begin not by axiomatizing the whole real line, but just by axiomatizing this little infinitesimal object, and then say, well, once we've got one of these things, we look inside D to the D, and we pick out this submonoid, and we equip it with addition, and then we've got R. And so in theory, all the properties of the smooth reals might be axiomatized just in terms of D, which in principle would be an enormous simplification of this whole approach, but it's still at this stage at a very early it's still at a very early stage, and it's not at all clear that this program can be carried through. However, those are some of the different models of the continuum that one can consider in the Topos. There are many more, but I think I'm just about out of time, so I'll stop there.
Questions?
Could you say something about the universal properties of the Dedekind and Cauchy reals?
Do they have any universal properties?
That's one message.
Not known to me. I mean, the Dedekind reals one would like to be the order completion of the rationals, but they're not. The Cauchy reals, I suppose, in some sense, they are. If you formulate it correctly, they're the metric completion of the rationals. But again, that's not a terribly useful property, I don't think. And I don't think it's a helpful way of thinking about them, actually.
You mentioned that the formal reals are spatial if and only if what was it again? The Dedekind reals with addition are spatial.
Reals are locally compact, yeah.
Can you also say something about the Dedekind reals with multiplication?
Sorry.
So I had a condition that the Dedekind reals with addition are spatial group is equivalent to something.
Oh yeah. Right. Well, I mean that's a sort of accidental result. That it depends on facts about localic groups, So the reals are a group under addition, and for them to be a localic group, they would have to be locally compact. Of course, under multiplication, they're only a semigroup or a monoid, and that result is special to groups. It doesn't hold for monoids. So I don't have an analogous condition on the multiplicative structure. No.
Are there any Topos approaches to say what is a manifold, or would it all be done more in the synthetic way than that static kind of way?
Well, in the world of synthetic differential geometry, of course, once one has axioms of the real line, one can extend those to axioms of manifolds in a very straightforward way. I don't see what one would mean synthetically by a manifold before one knew what the reals were.
Right, I was wondering, physically, we know that they don't have the zero and one. Well, I mean, tangent plane has a zero. They don't have the units and any kind of non-coordinate-free approaches.
Yeah, I mean, there is still scope, I guess, for a coordinate-free approach to the real line. I say, just choose 2 points and it becomes a ring. But you could also study the algebraic structure that it has without those 2 points, which, I guess you could axiomatize it that way, but it gets very much harder because you're working with unfamiliar algebraic structures.
I have a question actually. In our work and also in the work of the Dutch guys, it's quite typical that this condition that when you talk about Dedekind reals, the lower and the uppercut come arbitrarily close together is dropped. So in a sense we're talking about intervals there.
Yeah.
I know that it's somehow related to McNeil reals, this idea.
Well, I mean, if you drop the condition entirely, then you're axiomatizing a different space.
Yes.
Space whose points are the intervals in the reals.
Is there something? I mean, it's pretty easy to add to such intervals, if you like. That does make sense. But multiplication probably is even.
Multiplication will be hard.
Yeah, I guess.
Well, as I said, multiplication of Dedekind reals is hard.
Yes.
Constructively. It's not at all obvious how you do it.
Any further questions? So let's thank our speaker again.